Okay, so hello everyone. Welcome to LICD lecture number 41H. Today we are going to discuss multiple feedback filters concept. Then we will have a generalized derivation for transfer function, F naught and quality factor for a multiple feedback bandpass filter. Then we'll do the design of the same, that is multiple feedback bandpass filter, including the design steps and verification of the design values in LT Spice. Then next we will be discussing multiple feedback low pass filter, followed followed by the design of the same. Okay, so without further delay, let us start with the topic. Okay, so let us start now. Let me share my screen. Okay, so here it is. So let us begin. So multiple feedback filters utilizes more than one feedback part. So unlike their KRC counterparts, which configures the opamp for a finite gain K, you remember KRC filters have a finite gain K, which depends upon RA and RB registers. Multiple feedback filters exploit the full open loop opamp gain and also referred to as infinite gain filters. Okay, so we'll investigate the following multiple feedback filters: multiple feedback bandpass filter and multiple feedback low pass filter. So let us begin with the concept of a multiple feedback band pass filter. I think I have to divide this into two screens now because I will be discussing the diagram as well as the explanation together. So let me open both the screens. Okay, let me readjust it as per the view. Okay, I guess this much will be enough. And let me pull it down like this. Okay, so this is my multiple feedback band pass filter basically. Yeah, I guess it's proper now. So let us start analysis. Okay, let me make it 100 here. I think that will be better. Yeah. So the circuit which you see to your left hand side, let me adjust the. Okay, now it is proper. So the circuit you see here over here is a multiple feedback bandpass filter, and it is named after its inventor, that is Dalinis friend filter. It is also called as that. So the above circuit can be redrawn as follows, as it is shown over here. So here we have just tweaked the values, uh, tweaked the connections a little bit. So R2 and C1 is readjusted and drawn like this, because this will help us to solve the this thing very clearly. Okay, so over here R2 and C2 makes a differentiator. You see, it's an internal loop. R2 and C2 makes a differentiator, and here we can easily say by virtual ground concept that V plus is approximately equal to V minus. So these are the two things which we will take care of. Okay, right now. So we'll proceed over here. So what we are trying to do is we are trying to find the transfer function of the system. So here we'll first analyze C2 R2 opamp only, right? So separately, so it's a opamp differentiator. Here V out upon V1 is given by minus R2 upon XC2. Okay, here we are concentrating over here. Let me just open up the circuit over there also. Okay, so this is my opamp differentiator. We are concentrating on it right now. So over here we have R2 C2. R2 is the feedback resistor and C2 is the capacitor which is connected to the input and the inverting terminal of the op-amp. So the transfer function will be given by VO divided VO of S upon V1 of S will be given by minus R2 upon XC2, and XC2 is 1 upon S into C2. So your expression of VO in terms of V1 will be VO will be minus S times R2 C2 into V1. This is equation number 1. Okay, and we will apply the KCL at this node over here in this particular diagram. Let me slightly reduce it to 130, let's say. Yeah, so KCL at V1 gives us three things: I2, I1 and I3 all are incoming currents. So I1 plus I2 plus I3 will be equal to 0. So what is I1? V in minus V1 upon R1. What is I2? V0 minus V1 upon 1 upon SC1. And what is I3? 0 minus, or it is V minus minus V1 upon 1 upon SC2. So actually V minus is 0 because of virtual ground. So over here we rearrange the terms, and we separate out the terms of V in, and rest all the terms we keep on that side. We collect the terms for V1 and we collect the terms for V0. And now next, from equation number 1, we wherever there is a V1, we substitute it as V1 is equal to minus V0 SR2 C2. So we substitute that over here. So wherever there is a V1, we substitute it as minus V0 SR2 C2. So this expression becomes V1 upon R1 plus SC1 into VO plus V0 upon SR2 C2 into 1 plus R1 C1 plus SR2 R1 C2 R1, the whole divided by R1 is equal to 0. Now from this we rearrange the terms. So what we do is we collect all the VO terms together. So what we will get is this. Let me expand it a little now. Okay. So now V1, V in will be equal to, after this simplification algebraically, so we'll get equation number 2, H of S, which is the transfer function, which is VO of S upon V in of S, which will be given by S R2 C2 divided by 1 plus S R1 C1 plus S C2 R1 plus S square C1 C2 R1 R2. So this is the term which we will get with the help of equation number 2. Now we will convert this into frequency domain by substituting S equal to j omega. So H of j omega will be given by minus j omega R2 C2 divided by 1 minus omega square R1 C1 C1 R1 R2 C1 C2 plus j omega R1 into C1 plus C2. So this is my transfer function. So when we compare it with your standard transfer function of a bandpass filter, yeah, we don't have standard. Yeah, so this is the standard transfer function for a bandpass filter. We will able to get the terms, that is HOBP, then we will get Q and omega naught. So let us start comparing one by one. Now let me take it in one screen. Okay, so we are comparing these two terms. So what we will get over here is this, comparing equation number 3 and 4. This is equation number 3 and this is equation number 4. So comparing, we get this, that this term omega upon omega naught square. So here there is omega square, so this will be 1 upon omega square. So we'll get omega naught is equal to 1 upon square root of R1 R2 C1 C2. So F naught will be 1 upon 2 pi square root of R1 R2 C1 C2. This is the cutoff frequency of the bandpass filter. Now the second term which we will compare is this, j omega upon omega naught q. Here it is j omega R1 C1 plus C2. So here we'll compare it. So here j omega will cancel out, and q will be given by 1 upon omega naught R1 into C1 plus C2. So omega naught we already know from here, so we substitute the value over here. So finally we get the quality factor. If you solve it algebraically, you will get it as q is equal to square root of R2 upon R1 divided by square root of C1 upon C2 plus C2 upon C1 square root of. Okay, so this is my quality factor. Now the very last thing which we compare is the numerator. Numerator we have HOBP, right? Here we have HOBP is into j omega upon omega naught into q, right? And here we have it as j omega R2 C2 minus, and we have taken this side. So R2 C2 j omega will get cancelled out. So R2 C2 will be equal to minus HOBP upon 1 upon omega naught into q. So we know omega naught into q term from expression number A. See here, omega naught into q will be 1 upon R1 into C1 plus C2. So that's what we substitute over here. So 1 upon omega naught, here it is. Omega naught into q will be 1 upon R1 into C1 plus C2. So HOBP will be given by the expression minus R2 upon R1 in the numerator, and the denominator we have 1 plus C1 upon C2. Okay, and now we can substitute If we substitute C1 equal to C2 is equal to C, then omega naught will be 1 upon square root of R1 into C1 into C, because C1 and C2 are same as C, so it will remove from the it will get removed from the square root. So the new frequency will be 1 upon square root of R1 into R2 into C. Next value is Q. So if I have the values of C1 and C2 as same as C, so it will be square root of, here it will be 1 plus 1. So 1 plus 1, 2. So Q will be 0.5 into square root of R2 upon R1. Okay. And similarly, your HOBP will be minus R2 upon R1. Here we have both the capacitors as same equal to C. So it will be 2 over here in the denominator. So HOBP will be half of R2 upon R1. Also, HOBP can be written as minus 2Q square. So if you do this, you will get this expression simultaneously. Okay. Now let me see the corresponding design equations. So with this, the corresponding design equations from here, let me just bring it back. So these are the four equations which we got, correct? Omega naught, HOBP, and Q3 equations basically. So from here, we can rewrite the expression of R1, and that will be given by, these are the two design equations which we can get. So R1 will be 1 upon 2 omega naught into Q into C, right? And your R2 will be 2Q divided by omega naught into C. Okay, so how do we get it? How do we get these values? Let us concentrate here. So we have this relation Q is 0.5 into R2 square root of R2 upon R1. So Q square will be 0.5 square into R2 upon R1. So R2 will be R1 times Q square into 4. Right? And omega square is what? 1 upon R1 into R2 into C2 square. So here we can substitute it as 1 upon omega square C2 square into R1 will be R2. So here it is there R2. So if you once you equate the two, you will get R1 as 1 upon twice omega naught into QC. Similarly, we can get the value of R2 as 2Q into omega 2Q divided by omega naught into C. So if we denote the resonant gain magnitude as HOBP, for simplicity, we observe that it increases quadratically with Q. So if you see over here, HOBP is minus 2Q square. So it's increasing quadratically with Q. Okay. Now, if we want H naught as less than 2Q square, we must replace the R1 with a voltage divider like this. Okay. So this is the changes which we have to do. So in order to make H naught lesser than 2Q square. So if we not do that, then we will get back the same expression over here like this. So if we want H naught, that is the, I think, band pass gain actually. If we want that band pass gain to be lesser than 2Q square, so we have to divide this R1 as R1 of A and R1 of B like this. From this modification, you have to go over here. Okay. So then the design equations relatively will be R1 of A will be Q upon H naught into omega naught C, and R1 B will be R1 A times 2Q square divided by H naught minus 1. So with this, we can get H naught lesser than 2Q square. Okay. So this was one of the design suggestions. But even if you do not wish to do that, we can stick back to the above equations, right? And now we will see the design for a multiple feedback band pass filter with a resonant frequency of 1 kilohertz and a resonant gain of 20 dB. So a resonant gain of 20 dB means that 20 log to the base of 10 will be 20 dB. That means mod of HOBP will be 10. So HOBP is actually mod of HOBP is 2Q square. So 2Q square is equal to 10. So Q square is 5. So Q is root 5. Okay. And we know the formula for Q. Q is 0.5 into square root of R2 upon R1. So that is Q square will be 0.5 square into R2 upon R1, and Q square is 5. So if you equate the terms, you will get R2 as 20 times R1. So if you consider the value of R1 as 10K, So the R2 will be 20 times 10K, that will be 200K. So this is how we find the value of R1 and R2. Next, omega naught is given by the formula 1 upon square root of R1 into R2 into C. So that will be 2 pi f is equal to square root of R1 into R2 into C. So the capacitance value R1 and R2 value are known to us. F naught is known. So if after calculation, the C value is coming out to be 3.55 nanofarad. That will be C1 will be equal to C2 will be equal to 3.55 nanofarad. Okay. Hence your design circuit will be as follows. So you will have R1 and R2 as 10K and 200K respectively, and C2 and C1 as 3.55 nanofarad. Okay, so these are the uh, the values of resistors and capacitors which we are getting. Now let us check one more thing over here. Yeah. So gain HOBP can be a pretty high value if your quality factor is high. Okay, if your quality factor is, let's say, more than 10 or so HOBP will also increase quadratically. So that's why we can exploit the gain over here. Okay, so let us test this circuit in LT-Spice. So next I will open up the LT-Spice window. So the circuit is already made readily available for your reference. You all can also make that circuit within 2 minutes of your time. Okay, let me adjust this window now. Okay, so this is my multiple feedback bandpass filter. We have over here R2 which is 200K, C1 and C2 is 3.55 nanofarad, and R1 is 10K. Okay, and we have designed this for a frequency, a resonant frequency of 1 kilohertz and HOBP as 20 dB. So let us check this out. So I'll simulate this and I'll check the output, and don't paste plot. Okay, so let us check the highest gain over here. The highest gain is 20 dB, as it is very clear, and the cutoff frequency is also 1 kilohertz, as you can see very clearly. In the earlier KRC filters, you were not getting exactly precisely. If you remember, in the bandpass filter, you were getting a deviation in the the resonant frequency. It was supposed to be 1K. Let me see the design. It was supposed to be 1K, but it was deviating a little. And the resonant gain is also 20 dB at that value. So there is no denying that this is a better, much better design as compared to the second order KRC bandpass filter. Now, so your resonant frequency is 1 kilohertz, and the gain is also 20 dB. Okay, and now I think let's go to the next design now. So this is how this circuit will function as a bandpass filter. So it will pass a narrow band of frequencies. So maybe close to around 1K or so, and then it rejects all the other frequencies. So this is my pass band, and below the cutoff frequency and above the cutoff frequency, we have the stop band. It is basically a narrow bandpass filter. Okay, so I think we have completed this design. Next will we have completed this design. So yeah, F naught is 1 kilohertz and HOBP is 20 dB over here, as we have discussed. Next is multiple feedback low pass filters. Okay, so here there are very small changes as compared to the earlier part. Okay, let me open up the PDF. Okay, the circuit to your left hand side is the low pass filter multiple feedback. Onto your right hand side is my band pass filter. So what changes do you notice over here? R1 is same. Instead of capacitor C1, we have only C2 and C1, and R2 is present. Okay, so these are the changes which we have. So let us concentrate on the multiple feedback low pass filter. Okay, let me just keep the circuit open over here for a reference. Okay, fine. So let us continue. So this is the circuit for a multiple feedback low pass filter, and above circuit will consist of a low pass stage, that is R1 and C1, followed by an active low pass filter made up of R2, C2 and opamp. So basically this is your first order, like a low pass filter, right? And R3 alone allows control of quality factor. So R3 will actually control the quality factor, right? Now considering, let me just minimize it. So let me just focus on the inner circuit, that is R2, C2, and opamp. So here the input is V1, and this configuration is like an inverting configuration. So we have V out is equal to minus Z2 upon R1, Z2 upon R2, and Z2 is minus 1 upon S into C1 divided by R2 into V1. So what will be V0? V0 will be equal to minus 1 upon S into R2 into V1, S into R2 into C2 into V1. So V1 will be equal to minus V0 into V0 into minus of minus S R2 C2 into V0. That is the equation number 1. Okay, so this will remember. Next is follow the same procedure. So KCL at V1 will give us I1 plus I2 plus I3. I1 will be V in minus V1 upon R1, and I2 is V0 upon V1 divided by R3, and I3 will be 0 minus V1. Why 0? Because this is virtual grounded. So actually it should be V minus minus V1. So V minus is grounded, hence I'm saying 0 minus V1 upon R2. So these are the equations which we are getting. And over here I4 also is there. So I4, actually 4 currents, I4 will be 0 minus V1 into S into C1. Okay. So these are the values, various values of the equicurrents. So over here, if you club together the V in term, V out term, and V1 term, and we know from equation number 1 that V1 is given in terms of V out. So we resubstitute it over here. So V1 we resubstitute as R2 C2 S into V0. That the entire term is multiplied by minus sign. So we substitute it over here in place of V1, and we'll simplify it a little. I'll keep this open for 5 seconds so that you can pause and write. Okay, so let's continue. So we rearrange the terms. We finally get an expression of V out upon V in. That we will. Okay, this is double. Yeah. Okay, I guess page number 12 is missing somehow. So I'll get back that page number 12. So we have completed up here. V out upon V in is minus of R3 upon R1 into 1 plus S times C2 R2 C3 upon R1 plus C2 R3 plus C2 R2 bracket close in plus S square C1 C2 R3 R2. Okay, so after this, I think one page is missing. I'll just find out where it is. It is page number 12 actually. So not a problem. I will check it out. Just a minute. Okay, I guess I have got the page, so got a hold of it. Actually, so VO upon V in, this was in S domain, and now we substitute that in the frequency domain. So you will have minus R3 upon R1 divided by 1 plus j omega. This whole expression, whole term will come minus j omega. S is j omega, so j square will be minus 1. So it will be minus omega square C1, C2, R2, R3. So this is my transfer function of a multiple feedback low pass filter. Now if we compare this with the standard transfer function of a low pass filter, it will be HOLP divided by 1 minus omega upon omega naught square plus 1 upon omega naught into Q. So we'll compare this one by one, and HOLP will be directly minus R3 upon R1 without any effort. Okay. Next will be we will compare omega square. So minus omega square upon omega naught square will be equal to C omega square C1 C2 R2 C3. So that is what we have written over here. Okay, from here omega square will get cancelled out. Actually here it should be omega square should not be there. Okay, if it is there, then here also it should be there. Okay, let me just use the annotation. So over here also you should have omega square, so that you can cancel this term and cancel this term. So omega square will be 1 upon C1 C2 R2 C3. So this is the expression which we will get, and finally you will get omega naught is equal to 1 upon square root of R2 C3 into C1 C2. Okay, so that's the values which we are getting. And lastly, we can compare 1 upon omega naught q is equal to this entire term will come. 1 upon omega naught q will be equal to this entire term will come as it is. So that is equal to C2 R2 R3 upon R1 plus C2 R3 plus C2 R2. So q will be given by, we substitute the value of omega naught over here. So we will rearrange the terms and we'll get this finally this quality factor formula. Numerator we have square root of C1 upon C2. Denominator we have three terms, square root of R2 R3 R1 square plus square root of R3 divided by R2 plus square root of R2 divided by R3. So these are the three terms of quality factor which we have. Now, a disadvantage of this filter is that higher the value of Q and HOLP, greater is the capacitance spread. Okay, so we might have to have a higher value of capacitance spread if you have a wider value. I mean, capacitance spread means in the same circuit you have a very wide range of capacitance. That is what it means by it. Okay, so that's the only disadvantage. Now let's check this multiple feedback low pass filter. Okay, we have directly simulated one circuit and let's check that. This is not the design also you can carry out easily, not a problem, but let's check this circuit out. So this was band pass filter. Let me close this. I'll open a low pass filter. Okay, so this is my low pass filter. So low pass filter with a f naught equal to 10 kilohertz. Yeah, we can design it also. HOLP is equal to 10, Q is equal to 4. So these are the values which we are getting over here. Okay, so design is taken from Sergio Franco book. Okay, so that's the acknowledgement over there. And here are the values which are directly being calculated. You can also check it there. So these with these values, you will be surely getting a F naught of 10K and HOLP of 10. That will be a gain of 20 dB and quality factor of 4. So let's try it out. Okay. So these are the quality factor. Because of that quality factor, you have this overshoot. So gain over here will be close to, let's check the frequency value. So around 10 kilohertz, right? It's around 10.03, right? So 10.03 is my low cutoff frequency, and we require 10 kilohertz only. So we are getting 10.03. So our design is almost correct. Okay, so you can refer the design steps from this book. I think I have not given the design steps over here. Okay, no problem. You can similarly follow up the design steps from here. Okay, and you can refer this out. So that's it then. I think we have completed this entire topic of opamp filters. That is module number 3. So we started with, actually this should be feedback. Reverse motion. Okay, fine. So we started with actually the simple concept of passive filters, a long journey. I think I will be, let's say, reducing it. So let me go to the filter topics again. Okay, full screen mode. So there was a total 8 lectures in this module number 3, that is opamp filters. So we introduced filters with example, discussed active and passive filters, type of filters, the passive first order responses for low pass, high pass and band pass. Then we have gone to the first order low pass filter with opamp in inverting mode, then numerical and the design of the same, then first order high pass filter using inverting mode, then very important, first order active low pass filter and high pass filter in non-inverting mode. This is what we used in actual design, not the earlier one. Then the design of first order active low pass and high pass filter in the non-inverting mode. Then the first order band pass filter and its design. Then we introduced the concept of second order active low KRC low pass filter. We have derived the generalized transfer function for it, found out F naught and quality factor by comparing it with the standard transfer function. Then we designed this second order KRC low pass filter and high pass filter with equal component design and unity gain design. Then we also have seen the impact of quality factor on the second order low pass filter. We have also designed the second order KRC high pass filter using equal component design. And then finally, second order active KRC bandpass filter also we have seen its derive its formula for F naught and quality factor. Next, we have seen the concept of band reject KRC filter or a notch filter and design one circuit on based on it, notch filter. And last lecture, this lecture, we have completed multiple feedback filters concept. So generalized derivation for the expression of F naught and Q were derived explicitly for multiple feedback bandpass filter, and we have solved correspondingly one numerical on the same. That is a design of multiple feedback bandpass filter. Then we have also discussed the concept of multiple feedback low pass filter, and its design was taken from Sergio Franco book. Okay, I guess with this we have completed our module number 3, that is opamp filters. If you all have any query, you all can refer one of those videos. You can pause and stop and play and the video, whatever concept you have not understood. If still you all have any doubt, you all can always reach out via the email ID. Okay, so yeah, that's it for this module. So I think next time we will start with regulators module. Okay, regulators topic, module number 5. So everyone, thank you for patiently listening and watch those videos in the sequence one after the other. And I will request for you all to don't just observe the videos and directly use it. So practice it on a piece of paper, write it down, try it yourself, check the design values, build a circuit in LT Spice, and then you will attain that level of confidence. Okay. So that's it from the module of filters. I hope that this was a little bit of helpful in understanding filters module. So next time we'll start with regulators module. So until then, have a good day and thank you.